Hello, calculus fans. All right, let's look at an example where we have to use Taylor's inequality. So the problem is to find a third-order Taylor polynomial for f of x equals sine x centered at a equals 0. That is to say, we're looking for the Maclaurin polynomial. And let's place a bound on the error when we plug in values of x on the interval from -1/2 to 1/2. Now we know what the Maclaurin series for f of x equals sine x looks like. It's one of our known series. It looks like the sum where n goes from 0 to infinity of -1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. If you like to write that as something without the sigma notation, then we're looking at x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. Now we're interested in a third order Taylor polynomial, so we want just up to the third degree. So we could say that T3 of x is equal to x minus x cubed over 6. What does this mean? It means that sine x is approximately equal to x minus x cubed over 6. If you plug in values of x, sine x is about equal to x minus x cubed over 6. This approximation is pretty good when x is near 0. It becomes less good the farther out you go. Now we're interested in finding out how good this approximation is, at least on the interval from -1/2 to 1/2. Now we know that f quadruple prime is equal to sine x. You see, we need this because Taylor's inequality tells us that we need to find a bound on the fourth derivative. Why the fourth derivative? Because we're trying to do something with the third order Taylor polynomial. Now the fourth derivative is sine x, and on the interval from -1/2 to 1/2, or really any interval, we know that sine x is bounded above by 1. This is just a property of the sine function. So that means we're going to choose 1 in Taylor's inequality. All right, that's this guy. So let's write out now what Taylor's inequality tells us. So Taylor's inequality says that the absolute value of R3 of x is no bigger than 1 over n plus 1 factorial. Remember, we're using n equals 3 times absolute value of x to the 3 plus 1. So we can try to simplify all of this. This piece here is 1 over 24. And then the piece that's in here, notice that we're plugging in values of x between -1/2 and 1/2, so the absolute value of x is never any bigger than 1/2. And so that's how we get this piece here. And if you work all this out, you get 1 over 384. Now here's the important thing. This is better than anything that we've done before. What we can say is that no matter what value of x we pick in the interval from -1/2 to 1/2, the third order approximation will approximate the original function to within 1 over 384. Before, when we tried to do approximations, we had two problems. One is we had to do it for specific values of x, and we were also limited to doing it with the alternating series test. Here, we don't have that problem. Now, here's how you could test all this with your calculator. Choose any x you like on the interval from -1/2 to 1/2. Any x you want in that interval. Whatever you get there, the absolute value of that is guaranteed to be smaller than 1 over 384. So that works no matter what x you pick. Again, as long as you stay in the interval from -1/2 to 1/2. Okay, that's all for now.